Welcome to my complete CCNA Cisco Certified Network Associate course. This is Jeremy's IT Lab. This course aims to be a complete course for the CCNA, including everything you need to pass the exam, all 100% free. Stay tuned till the end of the video for the quiz to test your knowledge of the material in this video. Also, remember to download and use the Anki flashcards with the link in the description. Let's get started. This third lesson is about two networking models. The first is the OSI model, and the second is the TCP/IP suite. Note that the TCP/IP suite is a networking model too, but it's usually referred to as the TCP/IP suite or just TCP/IP. Unless you're familiar with networking, you probably haven't heard of the OSI model. However, you probably have heard of TCP/IP, or at least the second part of that name, IP, the Internet Protocol. For example, you've probably heard of an IP address before. So, what is a networking model? Well, networking models categorize and provide a structure for networking protocols and standards. Do you remember what a networking protocol is? I talked a bit about Ethernet and various standards for copper and fiber optic cables in the Day 2 video. That's an example of a protocol. A networking protocol is a set of rules defining how network devices and software should work, including how they should work together. By the way, protocols refer to logical rules about how devices should communicate, not physical standards. So you could visualize it like this. This is a networking model, and it categorizes and provides a structure for various networking protocols, like these. The different colors represent different categories of protocols and standards. These protocols and standards could define something like the structure and usage of IP addresses, or maybe physical details like electrical voltage used on copper cables when transmitting data. Let's talk about the OSI model first, and then we'll look at the TCP/IP suite after. So, what if there were no standard networking models and protocols? Here's a few Dell PCs, and a few iMacs. If Dell and Apple each made their own networking model, each with their own set of networking protocols, these Dells would be able to communicate with each other, and these iMacs would be able to communicate with each other, but because the Dells and iMacs would speak a different language than each other, with a different set of rules about how to communicate, the Dells wouldn't be able to communicate with the iMacs. This is obviously a problem in modern networks, such as the internet, where we expect devices from various makers in various countries to be able to communicate with each other. The OSI model is one attempt at standardizing network communications. Although it isn't actually in use today, it has had a big impact on how network engineers think about networking, and we still refer to it today. OSI stands for Open Systems Interconnection Model. Open means that it is an open standard, not a proprietary model developed and used by an individual company. It is a conceptual model that categorizes and standardizes the different functions in a network. It was created by the International Organization for Standardization, the ISO, in the late 1970s and early 1980s. Network functions are divided into 7 layers. For example, look at the bottom layer, layer 1. It is the physical layer. The standards for cables and interfaces we learned about in the Day 2 video all fit into the physical layer of the OSI model. But there are 6 more layers on top of that to make the network operate properly. Let's examine each layer one by one, starting at layer 7, the application layer. The application layer is the layer that is closest to the end user. The application layer interacts with software applications that have some communication component, such as your web browser, whether that's Brave, Firefox, Chrome, or whatever. For example, HTTP and HTTPS are layer 7 protocols. Notice HTTPS before cisco.com, indicating that HTTPS is being used to get this website and view it in the browser. Keep in mind that layer 7 doesn't include the application itself, like Chrome or Firefox, but rather the protocols that interact with the application, like HTTP or HTTPS. A couple functions of Layer 7 are identifying communication partners and synchronizing communication. Let me explain how it does this. Here I have two OSI model stacks, representing two computers that will communicate with each other. The software application, maybe a web browser, interacts with Layer 7, the application layer, and wants to send some data to the system on the right. This data is processed through the OSI stack, each layer adding something to the original data. This is called encapsulation, because the original data is encapsulated inside this additional information which is added on. By the time it reaches the physical layer, it is electrical signals on a wire and is sent to the neighboring system. Then the neighboring system performs the opposite process. The additions of each layer are stripped off until the data reaches the application layer of the neighboring system. This process is called de-encapsulation, as the additional information is removed as the data is processed up the stack. Both the encapsulation and de-encapsulation processes are examples of adjacent layer interaction between the different layers of the OSI model. However, the communication between the application layers of the two different systems is called same layer interaction. This same layer interaction between application layers is what allows the application layer to perform its functions of identifying communication partners, synchronizing communications, etc. Layer 6 of the OSI model is the presentation layer. Data in the application is in an application format, a format that applications understand. It needs to be translated to a different format to be sent over the network. The presentation layer's job is to translate between application and network formats. One example of a function of the presentation layer is encryption of data as it is sent, so that only the intended recipient can read it. And of course, decryption as it is received. The presentation layer also translates between different application layer formats to ensure that the data is in a format the receiving host can understand. To summarize, the presentation layer translates data to the appropriate format. That's all you really need to know about the presentation layer. Layer 5 of the OSI model is the session layer. The session layer controls dialogues, also known as sessions, between communicating hosts. It establishes, manages, and terminates connections between the local application, for example your web browser, and the remote application, for example YouTube. YouTube servers are being used by countless people at every moment, and there has to be a way to manage all of these sessions. That's the purpose of the session layer of the OSI model. So, we've looked at the top 3 layers of the OSI model. From top to bottom, application, presentation, and session. It's important to know what the functions of these layers are, but actually, network engineers don't really work with these layers of the OSI model. That is the job of application developers. Application developers work with the top layers of the OSI model to connect their applications over networks. Let's return to this diagram. Remember what I said about encapsulation? Well, data prepared at the top 3 layers is then sent over to the bottom 4 layers, which actually do the work of sending it over the network. After the top 3 layers hand data over to the bottom 4 layers, the next step before sending data is that layer 4, the transport layer, adds a header in front of the data like this. So, let's look into the transport layer a little bit. Layer 4 of the OSI model is the transport layer. It segments and reassembles data for communications between end hosts. To reword that, it breaks large pieces of data into smaller segments, which can be easily sent over the network and are less likely to cause transmission problems if errors occur. For example, if data wasn't segmented and you were trying to watch a video, if an error occurred that prevented the video from reaching your computer, you wouldn't be able to watch the video at all. However, if the data is segmented into many small units, and only one fails to reach the destination, that's not a big problem. The video might skip for a second, but then we'll continue on just fine. Also, the transport layer provides host-to-host communication, also known as end-to-end communication. This also provides process-to-process communications for applications. Now let's review. Data is prepared by the top 3 layers. A layer 4 header is added on. Note that at this point in the process, this unit of data plus layer 4 header is called a segment. Remember, if the data being sent is large enough, it will actually be segmented into smaller parts, and a layer 4 header will be added on to each segment. Next, that segment is passed on to layer 3, and another header is added on to the end, like this. Layer 3 of the OSI model is the network layer. The network layer provides connectivity between end hosts on different networks. For example, outside of the local area network, or LAN, which we mentioned briefly in the Day 1 video. Layer 3 provides logical addressing in the form of IP addresses, something you've probably heard of before. Layer 3 also provides path selection between source and destination. Often there are many possible paths which data can take to reach its destination, especially over a huge network like the internet. Layer 3 provides the means of selecting the best path. Routers operate at Layer 3. Remember in Day 1's video I said that routers are used when end hosts need to reach a destination outside of their LAN? That's because routers are Layer 3 devices. Let's review the encapsulation process again. Data is prepared by the upper layers. The transport layer adds a layer 4 header, and this combination of data plus layer 4 header is called a segment. Next, the network layer adds a layer 3 header, including information like the source and destination IP address to the segment. This combination of data, layer 4 header, and layer 3 header is called a packet. Next, the packet is further encapsulated at layer 2, this time with both a layer 2 header and a layer 2 trailer. Layer 2 of the OSI model is the data link layer. The data link layer provides node-to-node connectivity and data transfer. For example, direct connections between a PC and a switch, or a switch and a router, or a router and a router. Because layer 2 is adjacent to layer 1, the physical layer, it also defines how data is formatted for transmission over a physical medium, like copper UTP cables. Layer 2 also detects and possibly corrects errors that occur on the physical layer. Like layer 3, layer 2 also uses an addressing system. However, it is separate and different from layer 3 addressing. Finally, switches operate at layer 2. Switches look at the destination layer 2 address to determine where to send the data. Let's look at the encapsulation process once more. Data is prepared by the application layer. A layer 4 header is added to the data to make a segment. A layer 3 header is added to the segment to make a packet. Remember, the IP address is included in this layer 3 header. Then, a layer 2 header and a layer 2 trailer are added to the packet. At this point, the combination of data, layer 4 header, layer 3 header, layer 2 header, and layer 2 trailer is called a frame. Now, the data is not further encapsulated at layer 1. This frame is then sent over the connection, whether it's electrical signals over a wire or wireless signals in the case of Wi-Fi, to the neighboring system. Let's look at layer 1 of the OSI model a bit before moving on. Layer 1 of the OSI model is the physical layer. The physical layer defines physical characteristics of the medium used to transfer data between devices. For example, voltage levels, maximum transmission distances, like the maximum cable lengths mentioned in Day 2's video, physical connectors, cable specifications, etc. Digital bits are converted into electrical signals for wired connections, or radio signals for wireless connections like Wi-Fi. As I mentioned before, All of the information in Day 2's video, such as cables and pin layouts, is related to the physical layer of the OSI model. Okay, now we've got a complete frame, and that frame will be sent from the local device over this cable. Let's say it's an Ethernet cable. Once it reaches the remote device, the reverse process of encapsulation, de-encapsulation, takes place. The data link layer translates the raw physical data into a complete frame once again. Then the layer 2 header and trailer are removed, leaving the layer 3 packet. The layer 3 header is removed, leaving the layer 4 segment. Finally, the layer 4 header is removed, and we are left with the original data prepared by the upper layers of the original device. That's the process of de-encapsulation. Before moving on, I want to review some terms. So, when an application wants to send data to another system, it interacts with the application layer of the OSI stack, and the data is prepared to be sent. When the layer 4 header is added at the transport layer, what is this combination of data plus layer 4 header called? It's called a segment. Then, the layer 3 header is added on at the network layer. Remember, that includes the IP address. What's this now called? It's called a packet. Finally, a layer 2 header and trailer are added at the data link layer. What's this complete unit called? It's called a frame. Now, there is one new term that is used to refer to all of these. These are all called protocol data units, or PDUs. For example, segment is the term for a layer 4 PDU. Packet is the term for a layer 3 PDU, etc. By the way, at layer 1, the physical layer, the name for the PDU is bit, referring to the bits being transferred on the wire. So, that's a lot of information. If you need help remembering the order of the OSI model layers, the flashcards included in the description should be a big help. But here are a couple acronyms too. I don't use acronyms to remember things myself, but many people like them, so here are a few examples to help you remember. The first one goes from layer 7 to layer 1. All people seem to need data processing. Here's another one from layer 1 to layer 7. Please do not teach students pointless acronyms. If you know any other good ones, please post them in the comment section. Now let's move on from the OSI model to the TCP/IP suite. Like the OSI model, it is a conceptual model and set of communications protocols, and in TCP/IP's case, it is used in the internet and other networks. It is known as TCP/IP because those are two of the foundational protocols in the suite. It was developed by the United States Department of Defense through DARPA, which is the Defense Advanced Research Projects Agency. It has a similar structure to the OSI model, but with fewer layers. And it is the model actually in use in modern networks, not OSI. Note, however, that the OSI model still influences how network engineers think and talk about networks today, which is why it's important to learn. Now let's compare the two. On the left is the OSI model you're familiar with by now. And on the right is the TCP/IP suite's networking model. The application, presentation, and session layers of the OSI model are essentially equivalent to the application layer of the TCP/IP model. Combining them into one actually represents how network engineers tend to think about networks, since we don't work much with anything above the transport layer. However, when talking about networks, we use the OSI numbering. For example, if you say there is a layer 4 problem in the network, network engineers will think of OSI's layer 4, the transport layer, not TCP/IP's layer 4, the application layer. Moving on, the OSI model and the TCP/IP model both share the transport layer. The network layer of the OSI model maps to the internet layer of the TCP/IP model. Finally, the data link and physical layers of the OSI model are equivalent to the link layer of the TCP/IP model. Once again though, if people say, for example, there is a layer 2 problem in the network, they are referring to the OSI model's layer 2, the data link layer, not TCP/IP's layer 2, the internet layer. Keep that in mind. Although TCP/IP is the model actually in use in modern-day networks, we still talk about networks using the OSI model language. Now, you might hear different names used for these layers. This is a chart off of Wikipedia, showing different naming systems used. Don't worry about memorizing all of these, but just keep in mind you might hear different names than the ones I taught you. For example, the link layer might be called the network interface or network access layer. I actually like this 5-layer model because it combines the top 3 layers that we, network engineers, don't really think about into one. But it keeps the data link and physical layers separate, and I think it's good to think of them as 2 separate layers. Before finishing up this lesson and moving on to the quiz, I want to show you this excellent diagram which I found on Wikipedia. It demonstrates the process of a host, host A, sending data to host B, with 2 routers in between. Here you see the 4 devices. Host A connected to a router, connected to another router, connected to host B. Here is the TCP/IP stack on each device. Note that, for forwarding data from host to host, these routers don't need to be aware of the higher layers, so only the internet and link layers are present here. So let's walk through the process. An application on host A wants to communicate with an application on host B. Let's say it's a Skype conversation, so host A is sending a little bit of video and audio data to host B. Skype interacts with the application layer, and data is encapsulated via the transport, internet, and link layers. Then, it is forwarded over to the router, probably via Ethernet UTP copper cabling. Remember, routers are layer 3 devices, so they want to know the layer 3 IP address to know where to forward the data next. So, de-encapsulation occurs at the link layer, and then at the internet layer, the router looks at the destination IP address to know where to send the packet. Then, the packet is once again encapsulated to make a frame. From here, it is sent to another router, perhaps over long-distance fiber cabling. At the link layer of the second router, de-encapsulation occurs again, and this router also checks the destination IP address. Once it knows where to send the packet, it is once again encapsulated and sent over some medium, Ethernet cabling in this case, to host B. Now, de-encapsulation takes place once more. Here at the link layer, it is a frame. The header and trailer are removed, and it becomes a packet. The header is removed, and it becomes a segment. Finally, the transport layer header is removed, and the application layer on host B receives the data and interacts with the application on host B. So, this has achieved process-to-process communication between Skype on host A and Skype on host B. Of course, this process will happen many times in both directions during the duration of a Skype call. As I mentioned before, this is known as same-layer interaction. Also, I mentioned the transport layer provides host-to-host communications before. This diagram indicates that as well. This transport layer segment was never changed during this whole process. It is as if it's direct communication between the 2 hosts. Finally, remember that because the TCP/IP protocols are all industry standard protocols used by all makers, it doesn't matter what kind of PCs or router you're using. An Apple iMac can communicate with a Cisco router, which can communicate with a Juniper router, which can communicate with a Dell PC. That's the importance of having industry standards. Okay, that was another lesson with a lot of information. Once again, there will be supplementary materials to help you remember everything. There will, of course, be an end-of-video quiz coming up from the next slide. There will also be pre-made flashcards to help you memorize what you need to remember. Check the link in the description. Finally, for this video I will again include a packet tracer practice lab, which will use an interesting feature of packet tracer called simulation mode to analyze network traffic. Now let's go to the quiz. HTTP data sent from a YouTube web server is displayed via your web browser. This is an example of what? A. Adjacent layer interaction. B. Same layer interaction. C. Encapsulation. Or D. De-encapsulation. Pause the video to think about your answer. The answer is B. Same layer interaction. Let's check the options. Adjacent layer interaction refers to interaction between different layers of the OSI model. In this case, both YouTube's web server and your web browser are operating at layer 7 using HTTP. So A, adjacent layer interaction, is incorrect. Although encapsulation and de-encapsulation of data surely happen many times as the data was sent from YouTube's web server to your web browser, they are not descriptions of the interaction between YouTube and your browser. So C, encapsulation, and D, de-encapsulation, are incorrect. Same layer interaction refers to interaction between the same layer on different hosts. In this case, the application layer of YouTube's web server and the browser on your PC. The concept of same layer interaction allows you to ignore the other layers involved and focus on interactions between a single layer on different devices. So B, same layer interaction, is the correct answer. Let's go to question 2. HTTP data has been encapsulated with 3 separate headers and 1 trailer. What is the appropriate name for this PDU? A. Packet. B. Segment. C. Frame. Or D. Data. Pause the video to think about your answer. The answer is C. Frame. Let's check. Packet refers to the OSI Layer 3 PDU. It would have 2 headers, the Layer 4 header and the Layer 3 header, and no trailer. So A, packet, is incorrect. Segment refers to the OSI Layer 4 PDU. It would have 1 header, the Layer 4 header, and no trailer. So B, segment, is incorrect. Data refers to the upper layer data before being encapsulated. It would have no headers or trailer. So D, data, is incorrect. Frame refers to the OSI Layer 2 PDU. It has 3 headers, Layer 4, Layer 3, and Layer 2 headers, and 1 trailer, the Layer 2 trailer. So C, frame, is the correct answer. Let's go to question 3. Which layers of the OSI model are most relevant to the role of a network engineer? A. Transport, network, data link, and physical. B. Transport, network, and data link. C. Network only. Or D. Application, presentation, and session. Pause the video to think about your answer. The answer is A. Transport, network, data link, and physical. Let's check. Although these layers are very relevant to the duties of a network engineer, the physical layer is missing. So B, transport, network, and data link, is incorrect. Although the network layer is very relevant to network engineers, of course, it is not the only one. So C, network only, is incorrect. These layers of the OSI model are not generally relevant to the role of a network engineer. They are relevant to application developers. So D, application, presentation, and session, is incorrect. These 4 lower layers of the OSI model are all very relevant to the role of a network engineer. So A, transport, network, data link, and physical, is the correct answer. Let's go to the next question. The link layer of the TCP/IP model is equivalent to what layer or layers of the OSI model? A. Transport and network. B. Network and data link. C. Data link. Or D. Data link and physical. Pause the video to think about your answer. The correct answer is D. Data link and physical. Let's check. The OSI transport layer is equivalent to the TCP/IP transport layer, and the OSI network layer is equivalent to the TCP/IP internet layer. So A, transport and network layers, is incorrect. The OSI network layer is equivalent to the TCP/IP internet layer. The OSI data link layer is equivalent to part of the TCP/IP link layer, but it is not totally equivalent. So B, network and data link layers, and C, data link layer, are incorrect. The combined functions of the OSI data link and physical layers are equivalent to the TCP/IP link layer. So D, data link and physical layers, is the correct answer. Let's go to the last quiz question for this video. Which layer of the OSI model provides host-to-host communications? A. Application. B. Network. C. Transport. Or D. Data link. Pause the video to think about your answer. The answer is C. Transport. Let's check. The application layer provides process-to-process communications, not host-to-host. So A, application layer, is incorrect. The network and data link layers do not provide end-to-end, host-to-host communications. So B, network, and D, data link, are incorrect. The transport layer provides host-to-host communications, as shown in this diagram. So C, transport, is the correct answer. Thank you for watching. That's all for this video. If you want to show your support, please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. I accept donations via cryptocurrency or Patreon via the links in the description. I'm also a Brave verified publisher and accept BAT, or Basic Attention Token, tips via the Brave browser. Click the link in the description to check out Brave, a fast and sleek browser that pays you to surf the internet. That's all for now.